Hi, my name is Camilo Perez. I'm a master's student at McGill University. I'm here today to present the paper, a new simulation model for multi-agricultural biomass logistics system in bioenergy production. Canadian pears have a unique opportunity to become key players in the biofuel industry due to high biomass availability, especially agricultural residues. But with every opportunity there's a challenge, and in this case the challenge is logistics. The logistic cost is around 40 to 60% of the total operational cost, and studies have shown that by minimizing the logistic cost to 25%, the operational could become feasible. That is why simulation and modeling is required to optimize the supply chain. The supply chain from all around the process. With this in mind, the objectives are basically three. First is to define if the bioethanol plant daily requirements could be met with the current supply chain model. Second, to calculate the optimal storage facility as well as the equipment requirements. And third is to calculate the logistic cost. Now we're going to see the case study. The case study is Iogen Corporation wanted to build a bioethanol plant at Prince Albert region at Saskatchewan. This bioethanol plant required 750 tons of biomass, and therefore this biomass will be acquired with 600 farms. This is the supply chain model that the paper is starting. Now the simulation model. IPSOL is the simulation tool. It uses input data from the users, such as weather, harvest schedule, crop yields, field data, equipment data, and resources. With this input data, they can run the simulations, and with these simulations, the output can be generated. Now we're going to discuss a little bit about the outputs. Basically, there are three outputs based on the conclusions. The first result is the demand fulfillment. The studies concluded that the daily demand of the bioethanol plant cannot be fulfilled. On average, 92% of the demand can be fulfilled throughout the year, especially from December to January. This is because poor weather conditions. The system is assuming that per every millimeter of rain or snow precipitation, the operation will delay between 1 hour to 2 hours, and with temperatures below -20, the operation will stop at all. So this is why the demand cannot be fulfilled. And now on the resource utilization, the storage capacity of at farm and at plant are calculated. At farm it was calculated at 400 tons and at plant 3,500 tons. On the equipment capacity we can see the number of equipment required in order to run the operation on a daily basis. And on the table we can see the dry matter losses and the utilization rate. This is important to take into account that in field transportation and loading into truck have low utilization rate. This is going to be talked a little bit further. On logistic costs, we can see that the square bailing and road transportation are two of the operations with highest logistic cost. And on the ethanol plant, we can see that the grinding is the highest operational cost, logistic cost. I'm sorry. The Durant width is the width with the less overall logistic cost, with $42.33 per ton. Now on the conclusions, the first conclusion is that better logistic coordination is required. The study showed that 29% of the biomass baled wasn't used in the bioethanol plant. This is something that it needs to be better coordinated. The second is the implementation of satellite storage location. By implementing this, the utilization rate of the equipment that we saw in previous slide will increase. Now, the third is the optimization of storage. The storage should be optimized in order to be able to operate throughout the year, even during winter. That way the throughput of the system will implement. Now I would like to thank my professor, my colleagues and my reviewers, and I want to thank you, and I'm open to any question that you may have. Thank you.